Okay, today's topic is electric potential, also known as voltage. As you'll see, initially learning electric potential is a little bit tricky, so let me begin by describing it to you first of all in the context of gravity. So first, let's start with gravitational potential. Okay, let's say that I first of all have right here the surface of the Earth. And then if you recall, near the surface of the Earth, we essentially have a constant gravitational field, which we represent as a series of field lines. Like so. So here in red is the Earth's gravitational field. Let's just refer to that as G. And then let's say I have an object, my marker, for example, of mass m, and I do work against gravity in lifting it to some height. When I do, I then therefore give the marker potential energy. If you recall from the first semester, the formula for potential energy U is mgh. So let's say I lift the marker to this height here above the ground. Okay, let's call this height here h1, and when I do, I then give the marker a potential energy U1 that's equal to mgh1. Okay, let's say that I instead now lift it to a greater height, h2, so then therefore it has a greater amount of potential energy, and we'll refer to that as U2. That would be mg times h2. So let's say that right here is that greater height. This right here is h2, and then the potential energy U2 is mg h2, like so. Okay, now let's focus in on, for a moment here, on the height h1. If I take the marker of mass m and I place it anywhere along that height, it's always going to have the same potential energy, mgh1. Let's say that I just want to talk about the height itself. The height itself, however, has the potential to have potential energy. I know that's a strange phrase, but if you do take the marker and place it anywhere along that height h1 above the ground, it will always have the same potential energy. Therefore, the height itself has the potential to have potential energy. Instead of saying that phrase, however, we shortcut this and we refer to it as gravitational potential. Gravitational potential is this quantity here, but what we do instead is we divide out by the mass m. That then gives us the following. Okay, so take the potential energy here and divide out by the mass m, and that then gives you this quantity here. This quantity here, gravitational potential, is measured in terms of joules per kilogram. Like so. Okay, now do the same thing here with the potential energy U2, where we're talking about height h2. If I take the marker and I place it anywhere along this height, it will have the same potential energy. Therefore, the height itself has the same potential to have potential energy, and once again, we refer to this as gravitational potential. So the gravitational potential is going to be this potential energy U2, and then divided by the mass m. That then gives us this quantity here. Now, h2 is greater than h1, so then therefore we say that this right here is a region of high potential, and then therefore this right here is referred to as a region of low potential. These regions of high and low potential, by the way, are referred to as equipotential surfaces. The surfaces are two-dimensional. So for example, right here at height h1, the equipotential surface comes out of the board at us like this. If I take the marker and I place it anywhere along that height, it has the same potential energy. So the height itself then therefore has the same amount of gravitational potential. That's what's referred to as an equipotential surface. Okay, here's a nice analogy of equipotential surfaces that you actually may be familiar with from a specific type of map that is used in earth science called a topographical map. Okay, a topographical map uses a series of what are called contour lines to represent changes in elevation, say above sea level, or changes in depth below the surface of the ocean itself if going down to the ocean floor. The individual contour lines themselves can be thought of as equipotential surfaces, specific heights. So on a topographical map, you'll see a contour line that represents a height, for example, of say 10 feet above the ground. Think of that as this equipotential surface. And then you would see another contour line that say represents 20 feet above the ground. That would represent another equipotential surface. So then therefore gravitational potential could be thought of by analogy as the contour lines on a topographical map. The difference between two regions of potential, the potential difference itself, this is the gravitational version of voltage. So the difference between these two is just simply referred to as a difference in gravitational potential. Okay, when talking about a gravitational potential difference, an object of mass m will always fall in a specific way. It will always fall from high to low potential. And now let's go ahead and extend this analogy here for gravity to talk about it in terms of electric fields, specifically now in terms of electric potential. Okay, so for electric potential, I'm now going to draw basically the same diagram as I did up on the top board. However, to produce that diagram on the top board now in terms of an electric field, now we'll think of the electric field produced in the following way. Let's say that right up here is a sheet of positive charge, like so. Let's say that down here is a sheet of negative charge. Therefore, we would then produce a constant electric field between the two sheets and would point downwards on the diagram, away from the positive charge and towards the negative charge, much like the gravity field that you see up on the top board. Like so. Okay, and then I take a positive test charge Q. Then let's say that I do work against the electric field and I raise it to some height here on my diagram. The height here, however, is usually referred to a distance. We usually refer to it as D. I'm going to use a D1 and a D2, like I did for H1 and H2 up on the top board. So let's say I take the positive test charge and I lift it to this height here above the negatively charged sheet. Refer to this right here as D1. Okay, when I do lift it to that height, I give it a potential energy, U1. Okay, then let's say that I lift it to a greater height on this diagram. Let's say to right here. This right here would be the height. We'll call this D2. Like so. And then therefore I give it potential energy, U2. However, like I did for gravity up on the top board, let's say that I wanted to divide out by the charge in this case and just talk about the height itself above the negatively charged sheet. In other words, I'm talking about the charge having the same potential to have potential energy anywhere along this equipotential surface. If I describe this, then what I am describing is electric potential. Electric potential is potential energy not divided by the mass m, but instead divided by the charge Q. Like so. When you do take potential energy and you divide it by the charge Q, you end up with an expression that is very similar to this expression here for gravity. But for gravity, it was the gravitational field multiplied by the height h1. In this case, it's the electric field E multiplied by the distance d1. Like so. And this quantity is referred to, as I said, as electric potential. It's the same thing as potential to have potential energy, That is its potential energy, U, divided out by the charge, Q. Okay, it's measured in terms of joules per coulomb. A joule per coulomb, however, is given its own name and symbol. It's referred to as a volt, which is just simply abbreviated as V. So the voltage, if you will, at this height above the negatively charged sheet is this quantity here. Okay, the voltage, however, up here at the greater distance D2, well, that would be the potential energy U2 divided by the charge. This would be equal to the electric field E multiplied by the distance D2, like so. Once again, this would be the voltage at this height here above the negatively charged sheet. Now, D2 is greater than D1, so then therefore, this right here is a region of high potential. And this right here is a region of low potential. And then, as I've already have previously mentioned, these guys right here are equipotential surfaces. Think of this as the electric field analogy, if you will, to a topographical map. On a topographical map, you're looking at gravitational equipotential surfaces. This is the electric field equivalent. These are electric potential surfaces, equipotential surfaces, that is, here for low potential and here for high potential. Okay, now, why didn't we really bother to describe all of this when talking about gravity, for example, back in the first semester? Why do we do so here in the context of electricity? Well, in terms of gravity, you only have one type of mass, and that's a positive value. And a positive mass is always going to fall downwards. That is, on the diagram above, an object that is released from rest will always fall from high to low potential. But there are two types of charges. There's positive and negative. A positive charge will fall on my diagram from high to low potential. It will get repelled by the positively charged sheet. It will be attracted by the negatively charged sheet. So then therefore a positive charge will fall downwards on the diagram. But the charge also comes in a negative variety, such as an electron, for an example. An electron falls backwards on the diagram. An electron falls from low to high potential. In other words, it's being repelled by the negatively charged sheet and attracted by the positively charged sheet. So an electron that is released from rest, for example, would fall upwards on the diagram like so. Okay, let me illustrate with a specific example here. There are two lecture examples. So go ahead and pause the film at this moment and copy down the first of those two lecture examples in your notes, and then I'll go through the solution here on the board. I'm going to erase the board, however, in the meantime. Okay, in the first of the two examples here, we're going to have a proton, and then secondly, an electron falling through an electric potential difference, a voltage of 5,000 volts. We'll begin with the proton, which falls downhill, if you will, from high to low potential. So to illustrate this first example here, I'm going to go ahead and just draw a constant electric field, much like I just erased on the board a few minutes ago. That is like so. So here's a negatively charged sheet. Here's a, oops, I got it backwards. Here's a positively charged sheet, excuse me. There we go. And then here's a negatively charged sheet. Okay, and then we have our electric field like so. Okay, and then I have two equipotential surfaces. Okay, right here we'll say is low potential. Right here is high potential. Okay, and then the difference between the two, the potential difference, is given to us. This is the voltage V. It's equal to 5,000 volts. Okay, so the proton accelerates from rest through this potential difference. So imagine taking the proton and starting it here at rest. V naught is equal to 0, and it then falls downhill from high to low potential. So it reaches this location here with some speed v that we're asked to calculate. Okay, now we're going to need some numbers here associated with the proton. First of all, its charge. Its charge is usually referred to as E plus, and this is 1.6 times 10 to the minus 19 coulombs. And then it also has a mass here. We'll just refer to the mass as m sub p for proton. This is 1.67 times 10 to the minus 27 kilograms. These are fundamental numbers associated with the proton. Okay, so first of all, in part A of the problem, we're asked to calculate its change in potential energy. Now, potential energy per charge is equal to voltage. So then therefore the potential energy is equal to the charge multiplied by the voltage. It's equal to the charge of the proton multiplied by the voltage V. So let me go ahead and calculate this number, and when I do, it's going to be quite small, and it's going to be in terms of joules. So I have to take the charge of the proton, 1.6 times 10 to the minus 19, multiply that by 5,000 volts, and this comes out to be 8 times 10 to the minus 16 joules. And then we'll just use a little bit of conservation of energy in part B of the problem to find the proton's final speed when it reaches this location here. Okay, recall that potential energy is equal to kinetic energy as the object falls. In other words, through conservation of energy, the initial potential energy U turns into the same amount of kinetic energy K when the object reaches its final position. Remember that the formula for kinetic energy is 1/2 mv squared, where the m here, once again, is the mass of the proton, m sub p. So let's just go ahead now and just take this portion of the expression here and solve for the speed v, cross multiply the 2, divide by the mass of the proton, and then take the square root. Once you do those couple of minor mathematical steps, you end up with this expression here. And now I'll just go ahead and plug in everything, where U, remember, is the potential energy that we just found a moment ago. So the U is still here in my calculator, so times it by 2, divide by 1.67 times 10 to the minus 27, and then take the square root of all of that. And when I do, it ends up being about 9.79 times 10 to the 5th or so meters per second. Quite fast. And now in part C, let's repeat the situation, repeat the problem, but now we have the negatively charged electron. Okay, the charge of the electron, it's usually referred to as E minus, is the same value as before, 1.6 times 10 to the minus 19 coulombs. The mass of the electron, I'll call it MCB, however, is considerably smaller than that of the proton. Here's the mass of the electron, it's another fundamental number. The mass of the proton is about 10,000 times bigger than this number here. However, on the diagram above, the electron, because it's negatively charged, falls upwards on the diagram. In other words, let me just redraw it like so. Okay, so once again, right here is the positively charged sheet. Here's the negatively charged sheet, like so. And then we have our electric field E. Like so. Okay, and then I have my two equipotential surfaces once again. Let's say right here is low potential. Right here is high potential. And the potential difference V is 5,000 volts. But in this case, the negatively charged electron falls upwards on the diagram. So release the electron from rest here, V naught is equal to 0, and then falls upwards on the diagram to here, arriving with some speed V. Okay, the initial potential energy of the electron is going to be the same formula as it was up on the top board for part A earlier for the proton. In this case, the potential energy is going to be the charge of the electron multiplied by the potential difference. But the charge of the electron is the same numerical value as it is for the proton, so then therefore the potential energy is the same number, 8 times 10 to the minus 16 joules. And then we'll once again do a little bit of conservation of energy, where all the potential energy turns into kinetic energy, but we're not going to end up with the same speed V here for the electron now, and the reason for that is because the mass of the electron is different than that of the mass of the proton. So I'm just going to go ahead and use this same formula here, but down in the denominator of the expression, we're talking about the mass of the electron instead. Like like so. And the mass of the electron is considerably smaller than that of the mass of the proton, so the speed here is going to be considerably larger. In fact, it's an appreciable portion of the speed of light, if I'm not mistaken. All right, so let me go ahead and calculate this out. So 2 times 8 times 10 to the minus 16 divided by the mass of the electron. Take the square root of all of that. And that comes out to be about 4.2 or so times 10 to the 7th meters per second. As I said, this is actually more than 10% of the speed of light in this particular case, okay? Okay, so once again, the reason why we bother to define difference in electric potential is because there are two types of charges, positive and negative, and this example illustrates the importance of that. Okay, let's take a look at the second example. Go ahead and copy it into your notes. Okay, let me do some erasing here. Here we're just going to do a couple of quick voltage calculations here for the second problem. Okay, so we have a uniform electric field of 300 newtons per coulomb. It points downwards on a diagram. So I'm just going to be drawing my diagram here exactly the same way as I did in the previous examples. Okay, let me just draw the field itself. Like so, and the magnitude here of the electric field is given to us as 300 newtons per coulomb. Okay, what is the potential difference between two vertical points that are the following distances apart? So we're taking a look at two different equipotential surfaces. Here's one surface here. Here's a second surface here. And the difference between the two we're just going to refer to as D. Okay, so from my description of potential difference earlier, potential energy per charge, which is equal to the voltage V, is equal to the electric field multiplied by the distance D. So then therefore, to calculate the voltage V, all that we have to do is take the electric field and multiply it by the different distances that are given here in the problem. All right, so in part A of the problem, the distance D is given to us as 5 centimeters. However, we do have to divide by 100 to convert this into meters to be in the proper units. This is 0.05 meters. So it's nothing more than 300 newtons per coulomb multiplied by 0.05 meters. When you do the units here, you end up with volts. So 300 times 0.05, 0.05, there we go. This comes out to be 15 volts. Okay, in part B, we'll just change it to 10 centimeters, which is twice as much. So then therefore, if it's twice as much, the potential difference there is just 30 volts. So it's like we're taking a look at like differences in height that are greater and greater on a topographical map. That's the easiest way to visualize what we're calculating. And then lastly, in part C, the distance D is 100 centimeters. That's 1 meter. So then therefore, the voltage V is going to be 300 volts, like so. So mathematically, we won't go any further than this when calculating out potential differences and so forth. Overall, however, mathematically, this is in fact a pretty advanced topic. You go through all the gory details of how to calculate potential difference for various types of charge configurations and all the calculus that is necessary to do that, like for example, in AP Physics C. Okay, at this point, I invite you to take a look at my screencast video, which uses a nice applet to show equipotential surfaces in 3 dimensions for a couple of different charge configurations. I've also posted a link for you for the applet itself in the folder. So that then concludes today's lessons. Make sure that you look over the rest of the materials in the folder. Today's shirt is Triptychon. See ya. Be safe.